last example in dynamics here for class 9. I picked this one because it ties the spring and the gravity potential energy together. It's sort of like a little weirdo problem here. This is from Tung, Benson Tung's book. He's got a funny name, Benson Tung. His last name's Tung. So the illustrated system is a simple model for analysis of animal gait. The linear spring models a body's ability to retain potential energy in the leg muscles during a stride. The block has a mass of 10 kilograms, and the spring constant of the leg is 14,000 newtons per meter. Assume that the entire system is traveling downward at a speed of 2 meters per second when the end of the uncompressed spring, free length of 0.5 meter, contacts the ground. What is the maximum compression of the leg spring? Right? So you can picture this thing. It's coming down, and then all of a sudden the spring touches, and now it's going to settle down to a certain level right there. And we want to figure out how far that's going to go, right? So let's see what happens in here. And you see that I say it's from Tung. So what we're going to do, we should... Whoop, that's the wrong one. Sorry. I decided that that one was actually too easy, even though this one's considered a level 1 and the other's a level 2. From Tung, he gave 2 different levels of problems. But I'm going to do this one instead. Okay, so we want to write out what this thing is at right here. So this is going to be the datum. So this right here is going to be the y. Let's say it's y2. That's the thing that we're going to try to find. Or maybe we're going to say, I don't know if I called it y1 before. We'll call it y1 to start with. It is the y1. Normally I would be calling it the y1, so that makes sense that I called it y1. Let me write this thing out. I usually write kinetic energy first. I started writing potential energy first. Kinetic energy plus potential energy. You can see that it's 9:30 at night right here, right? So what kind of maniac is still doing this stuff at 9:30 at night when he has another hour to drive home? I don't know. Something wrong with the kid. That's all I'm saying. So the kinetic energy in the beginning of the thing, okay, well, it's moving downward right here. So 1/2 mv1 squared. So 1/2 10 times the velocity of 2 meters per second squared. And we can actually find out this value. I think it's equal to 20. And these are Newton meters, by the way, in SI, right? Because this is a kilogram, this is a meter per second, but it's meter squared, second squared. So it's a kilogram, meter squared per second squared. Steal away one of those meters, and you got kilogram, meter per second squared. That's the definition of a Newton times a meter, right? It's that extra meter that was in there. Therefore, it's a Newton meter. The potential energy at 1 is going to be equal to the mass times gravity times that y1. Let's see that here in a second, what that's going to be. The spring is uncompressed, so we don't have to worry about it. 1 to 2, there's no losses taking place between states 1 and states 2, right there, right? So conservation of energy. We've been doing a lot of those. We need some more non-conservation ones. And then it's going to come to rest, right? It's going to come to where it stops. So the maximum compression is when this thing stops. So that we're put an explanation for next one. And now, so the potential energy at 2 is now going to be 1/2 k, and the amount of deflection that it has at 2 squared. Now, just the deflection is that it has at state 2 is equal to the datum of 1, right? So we can plug those things in here. So let's plug all this stuff in. I got 20 plus so let's say mg del 2, right? That's what we established right in here. that those two things were equal to each other. What is that weird little blue thing? I'm going to get rid of him, that little square thing. Anyway, not distracted. Okay, so the mass of it is 10 kilograms, 9.81, times our del 2, that's the thing we want to get, plus 0 for external stuff going on, 0 for kinetic energy, plus 1/2 K is going to be 14,000, and then we're going to have del 2 squared. You take a look here, and here's a scenario that I might have alluded to in a previous problem, where we're going to have a quadratic equation, right? This squared plus something times this plus or minus some type of constant right in here. So if I mess around with this thing, I'll write it in a standard format here. That squared minus 98.1, this del, and then minus 20 equals 0. So what do we do about that? Well, let's go ahead and find this by using negative b plus or minus the square root of b squared minus 4ac over 2a. We should memorize that now. Some of you probably have a calculator that has that pre-programmed in there, and you're just missing out on learning something in life, my friend. I don't know if that's true. Minus 4a 7,000. C is negative 20, right? So that negative gets rid of that negative, which is good for us because we don't want any imaginary numbers 2 times our 7,000. We will get 0.06092, and these are going to be meters. And we'll also get a negative 0.04690 meters. This is meaningless. How did it happen? I don't know. It's going to go up? I don't know. Maybe. Doesn't make any sense. So anyway, the answer to this is 60.9 millimeters. Boom. And but I did want to introduce at least one problem where we had this quadratic equation that shows up, and you can see what the scenario is that's caused this. That we have something where its gravity is changing due to position, but its potential so its potential energy to gravitational is changing by this, but then its potential energy because of springs is changing by the square. So that all results in having a quadratic equation, which is going to have 2 different roots to it, but only one of them is going to make sense. So 8 minutes.